Hi, in this video, we're going to take a look at setting up experiments. All right, so when this video, setting up experiments is kind of more broad than what we're going to talk about. Really, what we're focused on is that after I have my game plan for what I'm going to do with my data collection, I'm going to assign subjects to different groups. Now, we're going to do, two different ways. We're going to do random and we're going to do like a manual input aspect. I'm going to show you both of them. There's advantages and disadvantages of both of these. Random is the gold standard, but there are still pitfalls when we do random assignment, and we have to be aware of that as we design our experiments and set things up, because I might make a mistake with this just by random happenstance, and that could cause a problem with my experiment, and I wouldn't know until it's too late, if at all. All right, so we want to set up our experimental design so that we get the maximum benefit out of each data point that we collect. And so remember, design of experiments is to get the best experiments possible, do as little work as possible, get as much information as possible, get the least amount of bias, most accuracy, most precision, most interpretability and reliability in our data. All right, so there's some definitions we have to go over. So experimental design, this is a process by which specific conclusions are drawn about a hypothesis in an objective and controlled manner. The subjects are the individuals or items being experimented on. Could be people, animals, locations, users, anything like that. The treatment, all right, so this is a change given to one group, so like a new product, a new drug, a new intervention of some form. And then the control, this is a group not given any change, serving as a baseline. All right, so this baseline might be no treatment, nothing happening to them, it's just everything goes as is, or this could be like a well-established baseline medication. So imagine that I work for a pharmaceutical company, and I have a new medication that I want to try for disease. There's already an established medication, but I want to show that my medication is better. I'll give one group the control, which is the established baseline medication. I'll give another group my brand new medication, and then we'll run our experiment. So control may be no intervention, or it might be a baseline intervention that we are comparing the results off of. Now, a type 1 error is incorrectly rejecting the null hypothesis. So the null is correct, but we made a mistake. So we're concluding that there is an effect when there isn't. A type 2 error is when the null is incorrect. That is the alternative hypothesis is correct, and we made a mistake. We went with the null. There's advantages. There are risks anytime we're doing anything, right? And so if I'm doing an experiment, if I'm doing statistical analysis, I might reach the wrong conclusion. In experimental design, we need to fully understand what are the risks and what's what's the likelihood of making both types of errors, and what's the magnitude of the penalty for making the mistake. All right, so why use experimental design? Well, just to get better results, to do less data collection and get more meaningful data, to get good quality data that we can get results out of. All right, so experimental design is used across many fields, including medical research, marketing, product analytics, agriculture, government policies, business. I mean, it is used all over the place. All right, so let's talk about non-random assignment. All right, so right now on a project I'm working on, a team that I support with data analytics is running a non-random assignment, in that there's an established way of doing things. And for the project that we're working on, they changed something. And for 3 months, for a quarter, they've changed one thing in their process, and they want to see how do things play out. Now, this is not a scientifically rigorous experiment, but this is still going to give insight and information into what's going on. It's not feasible because of the business constraints. They need to continue delivering what they've already delivered, so they're modifying things just a little bit to be able to draw an inference on what's going on, because it's important for a larger project. It's not a random assignment. It is like a convenience assignment, honestly. A lot of times you'll see like convenience sample and statistics, anything that you just do without putting a whole lot of like rigorous setup into it, we'll call like convenience in data analytics. And so this is used far more often than it's given credit for. Now, if I need to do like scientific study where like the FDA is going to be analyzing the results of my work for a medication, if I want to submit academic papers, more than likely I need to have a more scientifically rigorous assignment process than just, hey, these guys are this one, these guys are this one, run with it. So it's super useful when I don't need that level of rigor, or that level of rigor is not possible. All right, so basically what we're going to do, we're going to assign two groups to different to two different treatments. And I misspelled something. There we go. And all right, so let's go ahead and run through this. So here, let's say that I've got two groups, and I'm just gonna break them up into two different. I've got this example I created. We have 500 sheep, and we got their weights, and I'm gonna break up my sheep into two groups, the first 250 and the second 250, and then I'm going to weigh them. All right. And so here, if there's just a complete randomness in the order of the sheep, then I'm going to just say 250, 250, and that's it. Maybe I'm by myself out on a ranch. I can't really handle the process on my own like like in a scientifically rigorous manner, and so this would be a way to just get inference into like subgroups. All right, and so now I'm pretending that weight is my response variable, and that this is something that I come up and I measure after I've made my decision that I've got two groups. And so I've got group one and group two, and I go through and I weigh all my sheep, and I check to see, is there a difference in their weights? Well, I mean, that's really, really tight, right? That's super tight. Standard deviation is just under 10 for both of them. The mean is really close to 75 for each. And so I will, any reasonable hypothesis test would fail to reject the null hypothesis and say that these two groups have the same, population average for weight. All right, and so like it's so close, I didn't even bother doing a t-test. Now let's do random assignments. All right, so now the important thing here for this lecture is notice how I assigned the groups, that I just went up and I grabbed the first 250, I grabbed the second 250. All right, so when I go up and I do this, remember that Python starts at 0. And when I do this interval, this is closed on the left, open on the right. So index 250 is not included in this data set. So notice that index 250 is not included. Now here, I'm going to start at 250. It's closed on the left. I'm going to go to the end of the data. So if whenever I have a colon, that is saying everything. If I have a colon, so let's say that instead I had colon 250, I'm saying everything up to 250. If I have 250 colon, I'm saying 250 and then later after that. And then regular colon is everything. And so this is a good way to work through things. Now, when I go through this iloc, so I think of index location. It's always rows before columns. Remember, whenever we're talking about like a matrix or a data frame, if I say 2, 3 as the location, that's the second row, third column. It's always rows before columns. And so it's rows. This indicates what the subsetting of the rows. And here we can see that we're getting all the columns on there. And that's how we do like index location. I don't know if that's the correct name. It's just I call it index location because that's easy for my head. If I did not have the I in there, LOC instead, then I would be using logical to determine the location, which I'll show you in a moment. Now for random assignments, what I'm going to do is I'm going to play the same game, and I'm going to just sample. Now this time, I am sampling the rows of the data. There's a couple different ways to do this. So here, when I use the sample function, I'm on a data frame. So remember, weights is a data frame, and I'm using the sample method on the data frame. I'm saying, hey, I want 250 of them. I can set up the random state. Hitchhiker's Guide to the Galaxy is why you'll see 42 over and over and over, by the way. Total, like that's true nerdhood, right? Hood right here. My advice to you is to, if you need repeatability, put in a meaningful number for your company. So let's say you're working for a company that was established in 1810. A lot of times I put 1810, or the company was put up on the stock market in 1996. I put in 1996. Do something like that where like all your stakeholders like know this number, and I find that that's an easy way to get people excited and interested in your work. They, they're kind of zoning off. They see that like, oh, why is it 1810? I know that number. And notice that I am replace is false because I want distinct rows. I don't want any duplicates. And then everything else, what I'm doing is I'm taking the index here and I'm saying drop it like it's hot from the data sets. And that gives me my two groups. Now, this is a way that I'm taking my data frame and I'm splitting it into two. I prefer to not split up my data frames. I like to keep one object and one clean data frame. My preference would be to keep everything into one data frame and have a column indicating the subgroup. But I want to show you both ways so that you have the tools. There's advantages and disadvantages both ways. All right, so now let's go ahead and compare the results. I'm not doing a hypothesis test yet, but we can see that I'm going to go through, I'm going to use the describe function on each of my subgroups on just the weight. And you can see I've got my mean, my standard deviation for each of them. And, just eyeballing that, I, failed to reject the null hypothesis. I conclude that the two groups have the same weights, which makes sense because they were sampled from the same normal distribution. All right, so non-random assignments. This is based off of like some predefined rules, business rules maybe. I mean, it could also be that we have like a reason for breaking up. There's a lot of different ways we could manually do it. And, this can result in unbalanced groups. If I don't like double check things, we can make mistakes. And we can also pick up features in our data that are not actually correct in the overall population. If I make a poor choice, kind of like that business rule example that I told you about with the team that I support. If it, so they're picking, 3 months to just try something different. Well, let's say they pick, the 3 months, and that was like the 3 months that, COVID kicked off, that there's some external other variable driving what happens, then they can't trust their data. Now, in that situation, everybody knows that COVID is happening, but you don't know that if there could be a covariate that's driving what's happening. We would like to have random assignment if possible, but there's still drawbacks because that random assignment, by random happenstance, could pick up features that aren't applicable to the overall population and make it look like we have results or don't have results incorrectly. And so, there's problems. All right, and now the smaller the data set, the more random assignment has an opportunity to just by happenstance, cause problems, and we won't know until it's too late, or if we ever know at all. And remember, when we're doing this assignment, this is before we collect our data. After we've collected our data, we're kind of committed to what we're doing. We've already put the time, money, and effort and stuff. It's hard for us to back out. We want to get it right the first time, especially important with small data. All right, so let's go ahead and let's just say that, for some, I've got data, and we go and we're going to just, run an example where non-random assignment can just cause problems. All right, so on this one, I'm going to sort my values on here. So let's say there is some process that the subjects, when I took their weight, for some reason they came in smallest to largest and I didn't catch it. I didn't notice it, or maybe the team that was working for me wasn't paying attention. Maybe they didn't really care about what's going on. Maybe they didn't know any better, or possibly there could be a fault in the measurement equipment, that as measurements happen over time, the device like kind of wears out and it starts giving me biased results. That could happen, right? And so here, imagine that just as some process that I was unaware of and was not caught, my measurements just happened to be sorted, smallest to greatest. Now, this is very extreme, but this is just to show you that non-random assignment can cause a problem. All right, so if I do, first 250, second 250, then the first group is going to have the smallest observations. The second group is going to have the largest observations. And clearly, we're going to reject the null hypothesis, even though I know when I generated the data, that's not the case. And so this is just going to highlight that there can be problems with this. All right, so check this out. I've got a mean of 66 and a mean of 82. All right, I mean, that's a pretty decent difference. Also, you notice my standard deviation dropped down to 6 for both of these. All right, these are tighter groups, and they've got, they've split in their average. So let's go ahead and take a look at the picture. All right, so I know because I generated the data that it should just be a bell shape. If we did random assignment, I would have two, approximately equally distributed histograms. But pretending that I'm using this as a simulation of an actual experiment, because of the process that I was unaware of that sorted my results, I said, hey, group 1, group 2, oh my gosh, look at this. It's amazing. I see such a large difference. It's not because of any real difference. It's because there was some mechanism that screwed up my experiment. And like a chump, I came up and I fully bit into that apple and got got biased results. All right, so now let's do this. Let's do another one. So this example shows where non-random assignment can cause problems. So by happenstance, I just happen to assign in a manner that goes along with some other event that happened. So the results, to my eyes, are one way, but in reality, there's something else. Let's go another direction. All right, so let's say that here's my response. Here's my treatment. Now, this treatment was assigned randomly. You notice that there's no real, solid pattern on this. This looks like a decent random sequence of it. If you don't believe me, take it and do like a run statistic to see if it's random. It's only 10 observations. So when I have smaller data sets, I have to be more careful about random assignment. Random assignment can happen to pick up on things that aren't actually there. Now, I know because I generated this data that there is no, let me show you. So we see, that we have a difference. It looks like it's a decent difference in there. I run my p-test and look, hey, look, right there, that's statistically significant. I would conclude that the two treatments have different averages. But I know because I generated this data and I manually did this, that this is not the case. These are actually all from the same distribution, but my random assignment just happened to pick up, larger and smaller for the two different groups. All right, so here I am incorrectly concluding that there is a difference when there isn't. So previously on the last one, we concluded that there was a difference when there wasn't. That difference was because of our partitioning method, not because of what we were actually trying to measure. Here we're concluding that there is a difference when there isn't, because we made a mistake on just how to do the random, we didn't make a mistake, but random assignment just happened to pick up features in the data. All right, and so here's the histogram just so that we can see what's going on with this. You can see that, we got some, larger negative values in the treatment 1 group comparatively. All right, so some practical considerations. Though we don't want to have uneven groups if we can avoid it. We want similar sample size as much as possible. That's not always feasible, especially if we're dealing with humans as subjects, that people will drop out and it might be it just doesn't work. Let's say that I had 2 treatments for cancer. One gives, one chemotherapy gives like horrible nausea and side effects. The side effects are much lighter. People, can drop out because of the effect of those side effects, and that can lead to uneven groups. Even though I did everything I could to have a good, solid, balanced study. Also, we can have imbalanced covariates. So here, there's some variable that's driving an aspect of our results, but we didn't catch it in our experimental design, and that can be a problem. And also we could have clumping of our subpopulations where, a particular subpopulation, outliers or anomalies, all just kind of land in one group when I have like random assignments. This is especially problematic when I have small sample size, and this can lead to incorrect conclusions. All right, so for your homework, what I want you to do, I want you to go and generate random values of a 10 by 2 data frame. So first column is going to be your group. Your second column is going to be your response. I want to use standard normal for the response. And I want you to generate random data frames until you get a statistically significant 2-sample t-test. Once you get a statistically significant 2-sample t-test, stop and submit that. I want you to see that by random chance, you can come up with incorrect results. Now, both populations are standard normal, which means we should not conclude that there is a difference. That's the correct conclusion. I want you to generate a data set where you reach the wrong conclusion, just so that you are aware of the weaknesses of random assignment. That's all I've got for you. Life is short. Do math.